So today I'll talk about thickness and its applications. So let's start with some background. We all know that contour sets are important sets in analysis, topology, and in vector geometry. For example, we have the most well-known example, the middle third contour set. We start with the closed interval, remove the middle third, and repeat indefinitely, and we'll obtain a contour set. And this is an example of more general definition that we will use, which we define a contour set to be a compact, totally disconnected, and perfect subset of R. Although we know numerous things about contour sets, there are still some basic notions that we still fully do not understand. One of that is intersections of contour sets. So we can ask the following question. Take a middle third contour set, slightly translate a copy of it, and if we consider these two contour sets, the question is, will they intersect? And the answer is actually yes, and this directly follows from the fact that when we add two middle third contour sets, we obtain the full interval from 0 to 2. But we can ask a broader question. What if we change to general contour set and ask when would general contour sets intersect? It turns out that this is a very difficult question to fully answer. However, we can make a significant progress by considering the notion of thickness. So let us go back to our familiar middle third contour set. We're going to compute the ratio of what remains over what we have removed. So for example, we remove the first middle third, we compute the ratio of what remains on the left, remains on the right, divided by what we have just removed. So for middle third contour set, it's going to be 1. It's going to be 1 for the second gap, third gap, and so on and so forth. So even if we take the infimum of all those generations, it's going to be 1. And this is defined to be the thickness for the middle third contour set. This idea of thickness was first introduced by the mathematician Niehaus in 1970, where he defined, using this formula, the same formula, for all contour sets. And this is a very powerful notion because this actually allows us to answer the question when contour sets will intersect. And this is stated in the celebrated Niehaus lemma, which he also proved in 1970. It states the following. So take two contour sets whose convex sols are not disjoint. And if one contour set does not fall inside the gap of another contour set in a trivial sense, then whenever their product of thickness is big enough so that it's greater or equal to 1, then those contour sets are guaranteed to intersect. And we can generalize the middle third to the middle epsilon contour set and consider various examples. However, there's one thing that I want to make a remark on. This will be only guaranteed whenever the product of thickness is greater than or equal to 1. But when one of the contours that have thickness 0, this can never happen because the product will be always 0. So it would be very interesting to know and ask when contour sets with thickness 0 can possibly intersect with another contour sets. In order to answer this question, we have introduced the following lemma, which we call the containment lemma. So I'm going to use the following notation where intervals I and gaps U are going to be denoted by length and binary words consisted of 0 and 1. So 0 will be on the left-hand side, 1 will be on the right-hand side. So I get I0, I1, I00, I01, and so on and so forth. And our containment lemma is the following. So consider two different contour sets, C and C tilde. And now one of the convex sol of one contour set is going to be contained in the convex sol of another contour set, the larger contour set. So whenever we have the larger contour set to have smaller gaps for every generation, compared to the gap of the smaller contour set that is contained in the larger contour set, then this is enough to guarantee that those two contour sets will intersect. So how can we prove this containment lemma? We will use the induction to prove the following statement. The statement is that there exist nested sequences, sigma for I, sigma prime for C tilde, binary words, such that there is a sequence of intervals of C that's going to be contained in the sequence of intervals of C tilde. So this will happen for all generation, and C will be contained in C tilde for each intervals. So we first check the base case. This directly follows from our assumption that the convex sol of C is contained in the convex of C tilde. Next, we assume the induction hypothesis such that we have found such words, binary words, where the interval of C is contained in C tilde, just like in the end stage here. And now we're going to prove the induction step such that there's also inclusion in the next step. And here we recall our assumption, which states that the gap of the larger contour set is smaller than the gap of the smaller contour set. In this diagram, this implies that B tilde minus A tilde is less than B minus A, which in turn implies that A is less than A tilde, or B tilde is less than B. I've drawn the case where A is less than A tilde, and we can see that we have the inclusion in the next generation. So by the principle of mathematical induction, we have that this property will hold for all n. Now all we have to do is just take points that will lie inside the interval of one contour set. So their distance is bounded by the length of the interval of one contour set, and contour set is totally disconnected. So those lengths will go to 0 as n approaches infinity. And since contour sets are also compact, those limit points will lie inside C as well as in C tilde. And this means that C intersects C tilde is not empty. So we can now use this lemma, newly proven lemma, to answer the previous question. When we have thickness 0 contour set, we cannot use the Newhouse-Gap lemma, but we can now construct another contour set C tilde with larger convex hull but smaller gaps. And now those two contour sets are guaranteed to intersect. Now we use our lemma to two main applications. Our first application is on the algebraic sums of contour sets. So we define the sum of two sets in the usual sense, and then we consider some past results. For example, Steinhaus in 1920 proved that when those two sets have positive Lebesgue measure, then their sum will contain an interval. Feng and Wu proved in 2020, if we have n number of contour sets, all of them having positive thickness, then provided that their number is large enough, the sum of those contour sets will also have interval. However, note that we also require the thickness to be positive. So we can also ask, when would contour sets with thickness 0 contain an interval? And using our containment lemma, we can show that we can find such contour sets. And so this is our first corollary of our containment lemma. Secondly, we consider the error similarity conjecture. We first introduce a definition that we say a subset of R is called measure universal, or just universal, if all sets with positive Lebesgue measure contains a non-fine copy of it. So in a sense, a set is a universal pattern in all positive Lebesgue measure sets because we can take a copy of it and put inside all positive Lebesgue measure sets. Steinhaus again in 1920 proved that we can put any finite set in all positive Lebesgue measure sets, so they're universal. Based on this observation, this led Erdős to pose the following conjecture in 1974, which is now known as the Erdős similarity conjecture. He stated that it's going to be that infinite sets are not going to be measure universal because they're too large. We cannot put it inside all positive Lebesgue measure sets, and that would be impossible. There were a lot of attempts in the past. However, this conjecture still remains open for almost 50 years now. In order to make some progress and learn more about this problem, people started to consider topological versions for this conjecture, where they replaced the positive Lebesgue measure sets to be topologically large sets, so all dense G delta sets. So will there be a set, infinite set that we can put inside all dense G delta sets? Gallagher, Lai, and Weber have introduced this notion and also show that all contour sets are not topologically universal, using the notion of Hausdorff dimension. However, this proof was non-constructive. And using our lemma, we're able to provide a constructive proof for this result. Now I want to summarize my talk and consider some future questions. So thickness is a very powerful notion to measure the size of contour sets. And Newhouse-Gap lemma states that whenever the thickness is large enough, those contour sets are destined to intersect. However, the question still remained open for thickness 0 contour sets, and we answer that question using our newly proved containment lemma. And we consider two applications using that lemma. So our first open question is that given a contour set C, can we find another contour set C tilde such that they will intersect, but it will have Lebesgue measures? Can we find such a contour set? And secondly, can we generalize this to higher dimension Rn space? And lastly, can we find more interesting applications more interesting open problems that rely on Newhouse thickness, where we can apply our containment lemma. Thank you very much.
Are there any questions? I got all caught up in the topic. No, I have a question actually. Could you go back real quick to the measure universal property? Make sure I understand this correctly. The set is measure universal. All sets of positive vectors measure contain an affine copy of it. So by affine copy, you mean translation and maybe scaling?
Yes.
Okay.
For R1. In the higher dimension, there's more.
Sure. Okay. That was my question.
Good question.
Are there any questions, other questions for our speaker? I have another one then. Okay, so the proof basically produces at least one point that's in the intersection. Do you know how many there actually are?
That's a very good question, and as far as I know, I can't say much about it. But one thing I want to mention with regards to that is that, so this will note that this is translation invariant, because this only considers the size of gaps. So whenever the convex hull of one contour set is contained in the larger convex hull, I can actually slide the contour set inside, and it will maintain the intersection. But I cannot say what the intersecting set actually be. So I don't know if it's a contour set again or anything like that. It would be interesting.
Just wondering if, like, you know, if the nature of this beast is if you have one, you have infinity, like it's just not possible to have, you know what I mean? Okay, that's fine. I mean, I don't know anything about it, but it seems like it might happen. You know, I don't know how before. Are there any other questions for our speaker? All right, well, thank you again.